25 mind-blowing facts about the solar system that sound fake, but are true. Here's a strange truth about the place you live. Most of what's actually happening in the solar system sounds made up. Not exaggerated, made up, like something a screenwriter would get rejected for being too much. A planet that rains diamonds. A moon with more ocean than Earth. A world where the day outlasts the year. None of it is fiction. It's just physics, running for 4.5 billion years without anyone bothering to make it sound believable, and confirmed independently by spacecraft, telescopes, radar, and math that anyone with the patience can check for themselves. So let's go through the strangest, most solid, most checkable facts about our cosmic neighborhood, starting with the object that basically is the solar system, working out through the rocky worlds, the gas and ice giants, their moons, the small bodies drifting between them, and finally out to the true edge of everything we've ever charted. This is going to run long because the solar system genuinely earns it. Every stop along the way is backed by an actual measurement, an actual spacecraft, or an actual observation, not a rounded-up estimate dressed up to sound impressive. Let's get into it. Let's start at the center, with the star that doesn't just light the solar system. It basically is the solar system, gravitationally, chemically, and in terms of sheer bulk. Number 1. The Sun makes up 99.86% of all the mass in the solar system. Every planet, moon, asteroid, comet, and grain of dust floating out there combined accounts for the leftover 0.14%. Jupiter alone claims most of that sliver, roughly 2/3 of it. Earth, along with everything on it, is a rounding error in the ledger. If the whole solar system were a bathroom scale, you could remove every planet at once and the needle would barely twitch. Astronomers didn't just guess at this figure. They worked it out by watching how strongly the sun's gravity tugs on everything orbiting it. The bigger the mass, the stronger the pull, and the more precisely you can time an orbit, the more precisely you can back-calculate the mass doing the pulling. Kepler's laws, refined by Newton and later by radar ranging and spacecraft tracking, turned "how heavy is the sun" into one of the best measured numbers in astronomy, accurate to a tiny fraction of a percent. To put that dominance in a single image, if you built a scale model of the solar system using a basketball to represent the sun, Earth would be a peppercorn orbiting about 24 meters away, and Jupiter, the runner-up in mass, would still only be about the size of a golf ball. Number 2. The sun's core sits at around 15 million degrees Celsius, under pressure roughly 250 billion times what you feel standing at sea level on Earth. That combination is what makes fusion possible in the first place. Hydrogen nuclei, bare protons, repel each other ferociously because they carry the same electric charge, and under normal conditions they'd never get close enough to interact. But squeeze them hard enough, for long enough, and every so often quantum tunneling lets two protons slip past that repulsion and fuse anyway, kicking off a chain of reactions that eventually builds helium out of hydrogen and releases energy in the process. That energy is the ultimate source of every erg of sunlight that's ever warmed a planet, powered a photosynthetic leaf, or tanned a shoulder. The process is also spectacularly inefficient at the level of any single proton. A given hydrogen nucleus in the sun's core has, on average, to wait billions of years before it successfully fuses, which is precisely why the sun burns slowly and steadily instead of detonating all at once. Number 3. That energy has a genuinely strange commute. A photon born by fusion in the sun's core doesn't travel in a straight line outward. The interior is so dense that light gets absorbed and re-emitted, over and over, bouncing in essentially random directions each time. Physicists call it a random walk, and estimates for how long it takes a single photon to fight its way from the core to the surface, a distance of about 700,000 kilometers, run anywhere from tens of thousands to well over 100,000 years. Only in the outer third of the sun does energy transport switch from radiation to convection, with entire columns of plasma physically rising, cooling, and sinking again, like a pot of soup at a rolling boil, except each bubble of that boil, called a granule, is typically about the size of Texas, and a single granule only lasts around 8 to 20 minutes before it's replaced by the next one. Once a photon finally escapes the surface, it crosses the 150 million kilometers to Earth in about 8 minutes. In other words, the sunlight hitting your skin right now spent longer trapped inside the sun than most human civilizations have existed, and then covered the rest of its trip to your eyeball in less time than it takes to make coffee. Number 4. The sun is losing mass every single second, about 4 million tons of it, converted directly into energy by fusion, following Einstein's famous equation almost to the letter. On top of that, the solar wind, a constant outward stream of charged particles escaping the sun's atmosphere, carries away roughly another 1 to 2 million tons of actual matter every second, separate from the mass lost to fusion. It's been doing this for 4.6 billion years, and has enough hydrogen left in its core to keep going for roughly another 5 billion. Even at that rate, the sun has only burned through a small fraction of its total mass so far. You are, quite literally, standing in the exhaust of a star that is very slowly disappearing, just not anywhere near fast enough for you to notice, or for it to measurably affect Earth's orbit within any human timescale. Number 5. When you look at the sun, please don't actually look at the sun. You're seeing light that's already 8 minutes and 20 seconds old. That's how long it takes sunlight to cross 150 million kilometers of space to reach your eyes. If the sun vanished this instant, we'd keep basking in it for over 8 more minutes, completely unaware, and Earth would keep orbiting an empty point in space for that same stretch of time, since gravity's influence also travels at the speed of light, not instantaneously. This isn't just theory. The finite speed of light was first measured using data from the solar system itself. When the Danish astronomer Ole Romer noticed in the 1670s that eclipses of Jupiter's moon Io ran late or early depending on how far Earth was from Jupiter at the time, and correctly reasoned that light itself must take time to cross the gap. His original estimate was rough by modern standards, but the underlying insight that light has a speed at all, rather than arriving everywhere instantly, was correct, and it came from watching a moon of Jupiter, not from any experiment done on Earth. Number 6. The sun doesn't rotate as one solid piece, because it isn't one, it's a ball of plasma, and different latitudes spin at different speeds. The equator completes a rotation in about 25 days, while regions near the poles take closer to 34 days to come back around. That mismatch, called differential rotation, twists and stretches the sun's magnetic field lines like taffy, and the buildup and eventual snapping of that stress is what drives sunspots, solar flares, and the roughly 11-year solar cycle of rising and falling activity. In 1859, a solar outburst now known as the Carrington event sent a coronal mass ejection slamming into Earth's magnetic field so violently that telegraph systems across Europe and North America sparked, shocked operators, and in some cases kept transmitting even after being disconnected from their power source, running on induced current alone. Auroras during that storm were reportedly visible as far south as the Caribbean. A storm of that scale hitting today's power grids and satellite networks would be a global infrastructure event, not just a pretty aurora. A fact space weather agencies take seriously enough to monitor the sun around the clock for early warning. Number 7. Astronomers can see straight through the sun's opaque surface using sound. The convecting plasma inside the sun constantly generates sound waves, real acoustic vibrations, that ripple through the interior and cause the visible surface to oscillate up and down by tens of kilometers, in patterns that repeat every few minutes. By tracking millions of these overlapping vibrations, a field called heliosismology has let scientists map the sun's internal structure, layer by layer, the same way seismologists use earthquakes to map the inside of the Earth. It's how we know, independently of any nuclear physics model, that the boundary between the Sun's radiative and convective zones sits at roughly 70% of the way out from the core. And it's also how astronomers first got direct evidence that the Sun's interior rotates differently at different depths, not just different latitudes. Number 8. The closest any spacecraft has ever gotten to the Sun is the result of a genuinely extreme engineering problem. NASA's Parker Solar Probe, launched in 2018 and protected by a carbon composite heat shield only a few inches thick, has repeatedly dipped to within about 6 million kilometers of the Sun's surface, well inside the outer corona, where it endures temperatures around 1,400 degrees Celsius on its sun-facing side, while the instruments tucked in its shadow stay close to room temperature. In the process, it has become the fastest human-made object ever built, reaching speeds above 690,000 kilometers per hour during its closest approaches, fast enough to cross the distance from New York to Tokyo in well under a minute. Number 9. The Sun's fate is already written into its mass and composition. In roughly 5 billion years, once the hydrogen fuel in its core runs low, the Sun will swell into a red giant, likely expanding out to swallow Mercury and Venus and possibly grazing Earth's orbit, before shedding its outer layers into space as a glowing shell of gas called a planetary nebula. What's left behind will be an Earth-sized, impossibly dense core called a white dwarf, which will then just sit there cooling for trillions of years. Every star like the Sun in the galaxy follows this same basic script, and astronomers have watched other Sun-like stars at every stage of it, which is how we know our own star's future in the first place, not from guesswork, but from watching its cousins at every point along the same life cycle. Number 10. Even the Sun itself is orbiting something. Along with the rest of the solar system, it circles the center of the Milky Way galaxy at roughly 828,000 kilometers per hour, and still takes somewhere around 225 to 250 million years to complete a single lap, a span of time sometimes called a galactic year. The last time the Sun was in its current position relative to the galaxy's core, dinosaurs hadn't yet appeared on Earth. Every fact in this list, every planet and moon and comet, has been quietly riding along on that enormous, multi-hundred-million-year orbit the entire time. Now let's head toward the rocky planets, where the neighborhood gets small, fast, and considerably stranger. Number 11. A single day on Mercury, meaning sunrise to sunrise, lasts about 176 Earth days. Mercury's year, one full trip around the Sun, only takes 88 Earth days. That means a day on Mercury is twice as long as its entire year. Blame its lazy 59 Earth day rotation combined with a tight, fast orbit. The two stack together into a 3-2 spin-orbit resonance, meaning Mercury spins exactly 3 times for every 2 trips it makes around the Sun. That resonance produces an effect even stranger than the day-year mismatch. Because of the interplay between Mercury's fast-changing orbital speed and its steady rotation, an observer standing in the right spot on Mercury's surface near sunrise would actually watch the Sun rise partway, reverse and dip back toward the horizon, then rise again and continue on its way, a double sunrise caused entirely by orbital mechanics. Confirmed by radar observations of Mercury's rotation in 1965, that first revealed it wasn't tidally locked the way astronomers had assumed for decades. Number 12. Despite orbiting closer to the Sun than any other planet, Mercury has water ice. It sits at the bottom of deep craters near the poles that never see sunlight, staying permanently below freezing even while the sunlit ground nearby hits over 400 degrees Celsius. Because Mercury's axis barely tilts, those crater floors have stayed in permanent shadow for billions of years, cold traps sitting a few kilometers from some of the hottest surface temperatures in the solar system. NASA's MESSENGER probe confirmed the ice deposits with radar and neutron spectral data in the early 2010s, finding bright icy patches at the poles that matched decades-old Earth-based radar signals almost exactly. Number 13. Mercury carries an oversized iron core that takes up about 85% of the planet's radius, far more, proportionally, than any other planet's core. Earth's core, by comparison, only accounts for around 55% of its radius. Nobody fully agrees on why Mercury is so metal-heavy. Leading theories involve a colossal ancient impact that blasted away much of its rocky outer layers, or intense early solar heat that vaporized lighter material before the planet finished forming. Either way, the result is a small, dense world that's mostly a giant ball of iron with a thin, rocky shell wrapped around it. That iron core is still generating a real magnetic field, discovered by the Mariner 10 spacecraft in the 1970s, which came as a genuine surprise, since Mercury rotates so slowly that scientists didn't expect its core to churn fast enough to sustain a magnetic dynamo. It does, but weakly, at only about 1% of Earth's field strength, just strong enough to carve out a small magnetosphere that gets battered and reshaped constantly by the solar wind, since Mercury orbits so close to the source. Number 14. Mercury is shrinking. As its interior slowly cooled over billions of years, the planet's core contracted, and the surface had nowhere to go but to buckle and fold, producing towering cliffs called lobate scarps that snake for hundreds of kilometers across the landscape, some over a kilometer tall. MESSENGER's mapping data suggests Mercury's radius has shrunk by as much as 7 kilometers over its history, making it the planetary equivalent of a grape drying into a raisin, wrinkling as it loses volume from the inside out. Number 15. Mercury technically has an atmosphere, but it's so thin that scientists classify it as an exosphere rather than a true atmosphere. Individual atoms are more likely to collide with the ground than with each other. It's made mostly of atoms like sodium, oxygen, and helium, constantly knocked loose from the surface by solar wind particles and micrometeorite impacts, and just as constantly lost back to space, meaning every atom in Mercury's air is a temporary visitor. Sodium atoms in particular fluoresce under sunlight strongly enough that Earth-based telescopes can photograph Mercury's faint sodium tail, streaming away from the planet like a tiny comet. Now to Venus, Earth's near-twin in size that turned out to be nothing like Earth at all. Number 16. Venus's day is also longer than its year. One rotation takes 243 Earth days. One orbit takes 225. Venus somehow manages to out-weird Mercury on the exact same fact, and it doesn't rotate quickly enough in either direction to blur that distinction. Number 17. Venus doesn't just rotate slowly, it rotates backwards. Nearly every planet spins counterclockwise when viewed from above the Sun's north pole. Venus spins clockwise, meaning that if you could see the Sun through its clouds, it would rise in the west and set in the east. Nobody knows for certain why, though a massive ancient collision early in the solar system's history, or a slow tug-of-war between its thick atmosphere and its core, gradually tipping the planet over billions of years, are the leading suspects. Number 18. Venus is the hottest planet in the solar system, not Mercury, despite orbiting nearly twice as far from the Sun. Its surface averages around 465 degrees Celsius, hot enough to melt lead, thanks to a crushing carbon dioxide atmosphere roughly 90 times the pressure of Earth's, trapping heat in a runaway greenhouse effect. Mercury has no atmosphere to speak of, so its night side actually plunges to brutal cold, while Venus stays a blistering, uniform oven whether it's day or night, poles or equator. 90 times atmospheric pressure isn't an abstract number either, it's roughly what you'd feel underwater nearly a kilometer beneath the ocean's surface on Earth, except on Venus that crushing weight is sitting on open ground, made of carbon dioxide instead of water. Number 19. We only know what Venus's surface actually looks like because of radar. Venus is wrapped in a permanent blanket of clouds, thick enough that no optical telescope or camera has ever photographed its ground from orbit. NASA's Magellan spacecraft solved that problem in the early 1990s by bouncing radar waves through the clouds and reconstructing a global map from the echoes, revealing a surface covered in volcanoes, lava plains, and deformed highland regions. Reanalysis of that decades-old Magellan data, published in 2023, found direct evidence of surface changes near the volcano Mons consistent with an active eruption, suggesting Venus may still be volcanically alive today, not just scarred by an ancient past. Number 20. Venus is also where humanity first got observational proof that planets orbit the Sun rather than the other way around. In 1610, Galileo pointed his telescope at Venus and watched it go through phases, crescent to full and back, just like the Moon. That pattern is only possible if Venus orbits the Sun and sometimes passes almost directly between Earth and the Sun. Under the older Earth-centered model of the solar system, Venus couldn't show a full range of phases at all. It was one of the pieces of evidence that helped topple centuries of geocentric astronomy. Number 21. Venus occasionally passes directly across the face of the Sun as seen from Earth, an event called a transit, and these transits come in an odd, lopsided pattern, pairs 8 years apart, separated by gaps of over a century. In the 18th century, astronomers, including Captain James Cook's expedition to Tahiti in 1769, organized international efforts to time Venus's transit from multiple points on Earth, using the tiny differences in timing to triangulate the actual distance between Earth and the Sun for the first time with real precision. The next pair of transits won't occur until 2117 and 2125, meaning nobody currently alive is likely to see one. Now Earth and its moon, the one stop in this list you get to experience directly. Number 22. The moon is drifting away from Earth at about 3.8 centimeters per year, roughly the rate your fingernails grow. Billions of years from now, total solar eclipses as we know them will stop happening, because the moon will look too small to fully cover the Sun. We know this recession rate to a startling degree of precision because of retroreflectors, small mirror arrays left on the lunar surface by the Apollo astronauts and Soviet robotic landers, which let scientists on Earth bounce laser pulses off the moon and time the round trip down to fractions of a nanosecond. Number 23. The leading explanation for how the moon formed in the first place is the giant impact hypothesis, the idea that roughly 4.5 billion years ago, a Mars-sized protoplanet, sometimes called Theia, slammed into the young Earth at an angle, blasting a ring of vaporized and molten debris into orbit that eventually clumped together into the moon. It explains why lunar rock samples share such a strikingly similar chemical fingerprint to Earth's mantle, while also being depleted in the lighter, more volatile elements you'd expect to boil away in a catastrophic collision. Number 24. That same moon is likely doing more for Earth's habitability than most people realize. Its gravity helps stabilize Earth's axial tilt, keeping it wobbling within a narrow, relatively steady range, instead of swinging chaotically over millions of years, the way computer models suggest could happen to a planet with no large moon. A stable tilt means relatively stable, predictable seasons over long timescales, rather than the kind of wild climate swings that could make complex life's steady development far harder. Number 25. Earth's day is getting longer, and the moon is the reason. Tidal friction between Earth and the moon is gradually transferring rotational energy away from Earth, slowing its spin by roughly 2 milliseconds per century. Not enough to notice in a human lifetime, but very much noticeable over deep time. Growth ring patterns in fossilized corals suggest that around 620 million years ago, a full day on Earth lasted closer to 21 hours, meaning a year back then packed in roughly 420 days instead of 365. Number 26. What keeps Earth's atmosphere from being stripped away the way Mars's is largely its magnetic field, generated by the churning motion of molten iron in its outer core. That magnetic field deflects the bulk of the solar wind around the planet rather than letting it slam directly into the upper atmosphere. Mars, by contrast, lost its own global magnetic field billions of years ago, and data from NASA's MAVEN spacecraft shows the solar wind has been slowly sandblasting the Martian atmosphere into space ever since, a major reason Mars went from a plausibly wetter, thicker atmosphere world to the thin, cold desert it is today. Number 27. Not every solar eclipse looks the same, and the reason is the Moon's orbit isn't a perfect circle. Because the Moon's distance from Earth varies over the course of its elliptical orbit, sometimes it appears just barely large enough in the sky to fully cover the Sun, producing a total eclipse with the Sun's ghostly corona visible around the edges, and sometimes it's slightly too far away to fully cover the disk, leaving a blazing ring of sunlight visible around the Moon's silhouette, an annular eclipse, sometimes nicknamed a ring of fire. Which type you get on any given date depends entirely on where the Moon happens to be in its orbit that day. Onward to Mars, a planet that keeps setting records it shouldn't be allowed to hold. Number 28. Mars is home to Olympus Mons, the tallest known volcano in the solar system, standing about 21.9 kilometers high, roughly 2.5 times the height of Mount Everest above sea level. It's so wide, at nearly 600 kilometers across, that if you stood on its surface you likely couldn't tell you were on a mountain at all. The slope is that gradual. Part of why it grew so massive is that Mars has no shifting tectonic plates the way Earth does. The crust stayed put over a single hot spot for hundreds of millions of years, letting eruption after eruption pile up in the same place, instead of the volcanic activity getting spread across a moving chain of islands the way it does on Earth. Number 29. Mars also has Valles Marineris, a canyon system stretching about 4,000 kilometers long enough to cross the continental United States, and up to 7 kilometers deep in places. The Grand Canyon would fit inside it as a minor tributary, and scientists think it likely formed as the Martian crust cracked and stretched apart, rather than being carved primarily by water. Number 30. Mars has real seasons, driven by an axial tilt close to Earth's own, and its polar caps grow and shrink with them. Each cap is layered, a thin seasonal frost of frozen carbon dioxide, dry ice, that appears and vanishes with the Martian year, sitting on top of a permanent, much larger reservoir of water ice underneath that persists year-round. If all of that polar water ice melted at once, models suggest it would be enough to cover the entire planet in a layer of water several meters deep. Number 31. Rovers have found extensive evidence that Mars was once considerably wetter than it is now. Curiosity, exploring Gale Crater, found mudstone layered in a pattern consistent with a long-lived lake, filled and refilled over millions of years. Perseverance in Jezero Crater is investigating what looks unmistakably like an ancient river delta, complete with the kind of fan-shaped sediment deposits rivers leave behind on Earth when they empty into standing water. One of the reasons Jezero was chosen specifically as a place to hunt for signs of ancient microbial life, and Perseverance is currently caching drilled rock samples in sealed tubes on the surface for a future mission to eventually return to Earth. Number 32. Mars has two small, lumpy moons, Phobos and Deimos, and Phobos is on a genuine collision course, at least on cosmic timescales. It orbits so close to Mars, only about 6,000 kilometers above the surface, that tidal forces are dragging it inward by roughly 1.8 centimeters per year. In perhaps 30 to 50 million years, Phobos will either crash into the Martian surface or, more likely according to most models, get torn apart by Mars's gravity before it gets that close, scattering itself into a temporary ring around the planet. Number 33. Mars is also home to the most extreme dust storms in the solar system, capable of engulfing the entire planet in a haze that can persist for weeks. A global dust storm in 2018 blotted out enough sunlight that it starved NASA's solar-powered Opportunity rover of power. After 15 years of operation, far beyond its original 90-day mission, Opportunity went silent and was never heard from again. Number 34. We've actually held pieces of Mars in laboratories on Earth without ever launching a sample return mission, because ancient asteroid impacts on Mars occasionally blast surface rock hard enough to escape the planet's gravity entirely, and a small number of those fragments have eventually fallen to Earth as meteorites. One of the most famous, a meteorite known as ALH 84001, found in Antarctica, contains microscopic structures that sparked a fierce and still unresolved scientific debate in the 1990s over whether they might be fossilized evidence of ancient Martian microbial life. A claim most researchers now view skeptically, but one that helped launch much of the modern search for biosignatures on Mars. Between Mars and Jupiter lies a scattered ring of leftover material that never quite became a planet. Number 35. Despite how movies portray it, the asteroid belt is mostly empty space. The total mass of everything in the belt is less than 4% of the Moon's mass, spread across a region so vast that spacecraft have flown through it repeatedly without a single planned dodge, because the odds of hitting anything are astronomically small. On average, the asteroids inside it are separated by roughly 1 million kilometers apiece. Number 36. The belt isn't evenly spread out either. It has distinct gaps, called Kirkwood gaps, at specific distances from the Sun where an asteroid's orbital period would fall into a simple ratio with Jupiter's, like completing exactly 3 orbits for every one of Jupiter's. Objects that wander into those zones get a small, repeated gravitational tug from Jupiter at the same point in their orbit every single time, and over millions of years those repeated nudges add up, eventually flinging the asteroid onto a completely different orbit. The gaps aren't empty because nothing ever formed there. They're empty because Jupiter has been quietly sweeping them clean for billions of years. Number 37. The largest object in the asteroid belt series is big enough to be classified as a dwarf planet in its own right, and it's not the dead rock you might expect. NASA's Dawn spacecraft found mysterious bright spots inside Ceres's Occator crater that turned out to be deposits of sodium carbonate and other salts, left behind by briny liquid that welled up from underground and evaporated. A form of cryovolcanism, ice and mineral volcanism, that suggests Ceres may still have some liquid or slushy material beneath its crust. Number 38. The second most massive object in the belt, Vesta, is a fully differentiated body, meaning that early in its history it was hot enough inside to separate into distinct layers, a metallic core, a rocky mantle, and a basaltic crust. Essentially, the internal structure of a small planet rather than a lumpy asteroid. Chunks blasted off Vesta by ancient impacts have fallen to Earth as meteorites, giving scientists actual physical samples of the belt to study in laboratories without ever launching a sample return mission there either. Number 39. The asteroid belt isn't the only major asteroid population in the solar system, and it isn't even the largest one gravitationally tied to a single planet. 2 swarms of asteroids, called Trojans, share Jupiter's orbit entirely, clustered around points 60 degrees ahead of and behind the planet called Lagrange points, where the combined gravity of the Sun and Jupiter lets objects sit in a stable, long-term parking spot. Some estimates suggest the Jupiter Trojans may be as numerous as the asteroids in the main belt itself, and smaller Trojan populations have since been confirmed trailing and leading several other planets, including Earth and Neptune. Number 40. The asteroid belt is also a live planetary defense concern, not just a scientific curiosity. A roughly 10-kilometer-wide asteroid impact 66 million years ago near what's now Chicxulub, Mexico, triggered the mass extinction that ended the age of non-avian dinosaurs. In 2022, NASA's DART spacecraft deliberately slammed into Dimorphos, a small moonlet orbiting the asteroid Didymos, successfully changing its orbital period by over 30 minutes. The first time humanity demonstrated it could actually alter the path of an asteroid on purpose, a real proof of concept for deflecting a future dangerous impactor. Now for the giants, where scale stops making intuitive sense. Number 41. Jupiter's Great Red Spot, a storm that's been raging for at least 190 years and possibly far longer, is currently around 16,000 kilometers across, wider than Earth's own diameter of about 12,742 kilometers. You could drop our entire planet into that storm and still have room around the edges, though the storm has been slowly shrinking over the past century, and nobody is entirely sure when, or if, it will eventually dissipate. Number 42. Jupiter is more massive than every other planet in the solar system combined by a wide margin. At about 318 times Earth's mass, Jupiter alone accounts for roughly 2.5 times the combined mass of Saturn, Uranus, Neptune, and all the rocky planets put together. It's so large that its center of mass with the Sun, the barycenter both bodies technically orbit around, actually sits just outside the Sun's visible surface, rather than inside it the way it does for every other planet. Number 43. Jupiter's magnetic field is the strongest of any planet in the solar system, roughly 20,000 times stronger than Earth's, and the magnetosphere it generates is the largest structure in the solar system by volume, aside from the Sun's own heliosphere. If it were somehow visible to the naked eye from Earth, Jupiter's magnetosphere would appear larger in the sky than the full moon. Its tail, stretched out by the solar wind, extends past the orbit of Saturn. Number 44. That enormous gravity well makes Jupiter something like the solar system's bouncer. In 1994, astronomers watched, in real time, as the fragmented remains of comet Shoemaker-Levy 9 slammed into Jupiter's atmosphere one piece after another, punching Earth-sized scars into the cloud tops that remained visible for months. It was the first direct observation of an extraterrestrial impact on another planet, and a vivid demonstration of the role Jupiter's gravity plays in vacuuming up debris that might otherwise eventually threaten the inner solar system. Number 45. Jupiter has rings, though they're so faint and dark that they went completely undetected until Voyager 1 spotted them during its 1979 flyby. Unlike Saturn's bright, icy rings, Jupiter's are made of fine dust, likely kicked up by micrometeorite impacts on its small inner moons, and they're only visible at all under specific backlit lighting conditions. Number 46. As of recent counts, Jupiter has more than 90 confirmed moons, and the number keeps climbing as ground-based surveys find smaller and smaller ones. But the story of Jupiter's moons starts with just 4. In 1610, Galileo spotted Io, Europa, Ganymede, and Callisto through one of the earliest telescopes ever pointed at the sky, and watching them visibly orbit Jupiter rather than Earth was some of the first hard observational evidence against the idea that everything in the heavens circled our planet. Let's stay with those 4 Galilean moons for a moment, because each one is a world worth its own documentary. Number 47. Jupiter's moon Io is the most volcanically active body in the solar system, with over 400 active volcanoes, far more than Earth despite being smaller than our own moon. It's squeezed and flexed constantly by Jupiter's brutal gravity, along with tugs from neighboring moons Europa and Ganymede, generating enough internal friction to keep its surface in a state of continuous eruption, resurfacing itself faster than any other body we've observed. Some of Io's volcanic plumes have been photographed shooting material more than 300 kilometers above the surface, far higher than anything seen in a volcanic eruption on Earth. Number 48. Europa is believed to hold a liquid water ocean beneath its icy shell containing roughly twice the volume of water in all of Earth's oceans combined, on a moon smaller than our own. That ocean is kept liquid not by sunlight, which barely reaches it, but by tidal heating from Jupiter's gravity flexing the moon's interior, which is exactly why it's one of the top targets in the search for life beyond Earth. NASA's Europa Clipper mission, launched in 2024, is on its way to study that ice shell and ocean in detail, hunting for chemical signs of habitability without ever needing to land. Number 49. Ganymede is the largest moon in the entire solar system, bigger even than the planet Mercury, though it's less massive because it's made of a mix of rock and ice rather than being solid rock and metal. It's also the only moon known to generate its own internal magnetic field, distinct from Jupiter's, strong enough that it creates visible auroras in Ganymede's thin oxygen atmosphere. Evidence gathered by the Hubble Space Telescope and the Galileo spacecraft suggests Ganymede likely hides a saltwater ocean of its own, sandwiched between layers of ice deep beneath its surface. Number 50. Callisto, the outermost of the 4 Galilean moons, has one of the oldest, most heavily cratered surfaces of any object in the solar system, essentially unchanged for roughly 4 billion years. Unlike Io's constant volcanic resurfacing, Callisto's surface has barely been touched by geological activity since the early solar system, making it something close to a frozen time capsule of the bombardment every young world in the solar system endured. Now Saturn, the planet that looks the most like a cartoonist's idea of planet. Number 51. Saturn is the least dense planet in the solar system, with an average density lower than water, at about 0.69 grams per cubic centimeter compared to water's 1. If you somehow found a bathtub big enough, Saturn would float, rings and all, bobbing on the surface like a giant striped beach ball. Number 52. Saturn's rings span about 280,000 kilometers across, wide enough to fit the distance between Earth and the Moon, yet in most places they're only about 10 meters to a few hundred meters thick. Proportionally, they're thinner than a sheet of paper laid across a football field. They're made almost entirely of chunks of water ice, ranging from dust-sized grains to boulders the size of a house, all orbiting in a disk barely thicker than the objects inside it. Number 53. Nobody is entirely sure how old Saturn's rings actually are. For decades, astronomers assumed they were as old as the planet itself, roughly 4.5 billion years. But detailed mass measurements from NASA's Cassini spacecraft, which spent 13 years orbiting Saturn before deliberately diving into the planet's atmosphere in 2017, suggested the rings might be surprisingly young, possibly less than 100 million years old, meaning they could have formed sometime after dinosaurs already existed on Earth, likely from the shattered remains of an icy moon or comet torn apart by Saturn's gravity. Number 54. Saturn has a genuinely bizarre, persistent storm sitting right at its north pole, a 6-sided, hexagonal jet stream pattern first spotted by the Voyager spacecraft in the early 1980s and still there decades later. Each side of the hexagon stretches roughly 13,000 kilometers, wider than Earth, and the shape has stayed remarkably stable even as the storm inside it churns. Laboratory experiments simulating rotating fluids have managed to reproduce similar hexagonal patterns, tying the shape to the physics of jet streams at specific rotation speeds rather than anything mysterious. Number 55. Saturn's moon count has exploded in recent years thanks to improved ground-based telescope surveys. A single 2023 announcement added 62 newly confirmed moons at once, pushing Saturn's total past 140, and for now, ahead of Jupiter as the planet with the most known moons in the solar system. Most of these newly found moons are small, irregularly shaped bodies just a few kilometers across, likely captured debris rather than moons that formed alongside Saturn. Number 56. Two of Saturn's mid-sized moons look like nothing else in the solar system. Mimas has one impact crater, Herschel, so enormous relative to the moon itself, about a third of Mimas's entire diameter, that the whole moon has been nicknamed the Death Star Moon for its resemblance to the fictional space station. Ipetus, meanwhile, is two-toned, with one hemisphere dramatically darker than the other, likely from dark dust swept up from an outer moon encoding its leading face, and it also sports a bizarre ridge of mountains running almost exactly along its equator, tall enough in places to rival anything found elsewhere in the solar system, with no fully agreed-upon explanation for how it formed. Saturn's moon system also holds two of the single best candidates anywhere in the solar system for finding life beyond Earth. Number 57. Saturn's small moon Enceladus shoots geysers of water ice hundreds of kilometers into space from cracks near its south pole, fed by a liquid ocean hidden beneath its icy crust, making it one of the most promising places in the solar system to look for life. NASA's Cassini spacecraft actually flew directly through one of those plumes and detected organic molecules and hydrogen, the kind of chemistry that could support microbial life, along with evidence of hydrothermal activity on the ocean floor, similar to the vents on Earth's own seabed that host thriving ecosystems without any sunlight at all. Number 58. Saturn's moon Titan has lakes and seas, not of water, but of liquid methane and ethane. It's the only place beyond Earth known to have stable liquid on its surface, complete with a hydrocarbon rain cycle, rivers cut into its terrain, and shorelines shaped by hydrocarbon waves. Titan's largest sea, Kraken Mare, is estimated to hold more liquid hydrocarbon than all of Earth's oil and gas reserves combined. Number 59. Titan's atmosphere is thicker than Earth's, with surface pressure about 1.5 times what you'd feel at sea level here, and it's dense enough combined with Titan's low gravity, only about 14% of Earth's, that a person strapping a pair of wings to their arms could plausibly achieve human-powered flight there. The European Space Agency's Huygens probe actually landed on Titan's surface in January 2005, riding down through that thick orange haze on a parachute and transmitting images and data from the ground, the most distant successful landing on another world's surface ever achieved. Beyond Saturn, the solar system gets colder, dimmer, and if anything, even stranger. Number 60. Uranus rotates almost completely on its side, tilted about 98 degrees relative to its orbit. Instead of spinning like a top, it rolls around the sun like a ball, likely the result of an ancient, colossal impact early in its history. That extreme tilt means each pole gets around 42 years of continuous sunlight followed by 42 years of continuous darkness over the course of 184 Earth-year Uranian orbit. Number 61. Uranus has rings too, though they went unnoticed for centuries because they're dark and narrow rather than broad and icy bright like Saturn's. Astronomers only discovered them in 1977, and not by looking directly at Uranus at all. They were watching Uranus pass in front of a distant star, and noticed the star's light flickered and dimmed several times just before and after Uranus itself blocked it, revealing a set of narrow rings circling the planet that no telescope of the time could otherwise resolve. Number 62. Despite not being the most distant planet from the Sun, Uranus holds the record for the coldest planetary atmosphere ever measured in the solar system, plunging to about -224 degrees Celsius. The likely reason is that Uranus, unlike every other giant planet, radiates almost no detectable excess internal heat of its own, while Neptune, Jupiter, and Saturn all still glow faintly with leftover heat from their formation. Why Uranus lost that internal heat, possibly linked to the same ancient collision that tipped it on its side, remains an open question. Number 63. Uranus's moons break from the solar system's usual naming convention entirely. Instead of Greek or Roman mythology, They're named after characters from the works of William Shakespeare and Alexander Pope: Titania, Oberon, Miranda, Ariel, and Umbriel among them. Miranda in particular has one of the most chaotic-looking surfaces of any moon, a jumbled patchwork of terrains, including a cliff called Verona Rupes that may be as much as 20 kilometers tall, among the tallest known cliffs in the solar system. Number 64. Neptune was found before it was seen. Astronomers noticed that Uranus's orbit kept deviating slightly from what Newtonian gravity predicted, as if something unseen were tugging on it. Mathematicians Urban Le Verrier and John Couch Adams independently calculated where an unseen planet would have to be to cause exactly that wobble. And in 1846, astronomer Johann Galle pointed a telescope at the predicted coordinates and found Neptune within about 1 degree of where the math said it should be. A landmark moment for the predictive power of physics. Number 65. Deep inside Uranus and Neptune, scientists think it may actually rain diamonds. Under the crushing pressure and heat of their interiors, methane can break down and its carbon atoms can compress into solid diamond, which then sinks toward the core like hail. Laboratory experiments recreating those pressures with lasers have produced tiny diamonds in fractions of a second, lending real experimental weight to the idea. Number 66. A year on Neptune lasts 165 Earth years. Neptune was discovered in 1846, and it didn't complete its first full orbit since that discovery until 2011, meaning nobody alive today had been born the last time Neptune was in the exact spot astronomers first spotted it. Number 67. Neptune also has the fastest winds recorded anywhere in the solar system, with gusts measured at roughly 2,100 kilometers per hour, supersonic winds on a planet that receives less than 1,000th of the sunlight Earth does. Exactly where all that energy comes from, on a world so far from the sun's warmth, is still an open question for planetary scientists, tied to the same internal heat that Uranus mysteriously seems to lack. Voyager 2 also photographed a massive dark storm on Neptune in 1989, nicknamed the Great Dark Spot, roughly the size of Earth. But when the Hubble Space Telescope looked for it again just 5 years later, it was gone, and a new dark spot had appeared in a different location, showing that Neptune's storms can form and vanish on a timescale of just a few years, unlike Jupiter's centuries-old Great Red Spot. Number 68. Neptune's largest moon, Triton, doesn't belong to Neptune the way most moons belong to their planets. It orbits backwards, opposite to Neptune's own rotation, which is essentially impossible for a moon that formed alongside its planet. The leading explanation is that Triton is a captured object, likely a Kuiper Belt world much like Pluto, snagged by Neptune's gravity long ago. That backwards orbit is slowly decaying, and current estimates suggest that roughly 3.6 billion years from now, Triton will drift close enough for Neptune's gravity to tear it apart, most likely forming a spectacular ring system that could briefly rival or exceed Saturn's. In the meantime, Voyager 2 photographed active geysers on Triton's frozen nitrogen surface during its 1989 flyby, making it one of the rare moons confirmed to have ongoing geological activity, despite its extreme distance from the Sun. Voyager 2, remarkably, remains the only spacecraft ever to have visited Neptune at all, meaning everything else we've learned about the planet since 1989 has come from telescopes alone, and much of it is still an educated guess. Past Neptune, the solar system doesn't end. It just gets quieter and far, far bigger. Number 69. Pluto and its largest moon, Charon, orbit a point of balance that lies outside Pluto itself, which is why some astronomers call them a double dwarf planet system rather than a planet and a moon. NASA's New Horizons spacecraft flew past Pluto in July 2015 after a 9.5-year journey, and the images it sent back stunned planetary scientists. Rather than a dead, featureless ice ball, Pluto has a heart-shaped region called Tombaugh Regio, home to a massive glacier of nitrogen ice, Sputnik Planitia, that appears to be actively convecting, slowly overturning itself the way a lava lamp does, and possibly hiding a subsurface liquid water ocean beneath its frozen crust. Number 70. Pluto's atmosphere is so thin and so temperature-dependent that it's slowly freezing solid and falling to the surface as Pluto moves farther from the Sun along its elongated, 248-year orbit, only to sublimate back into a gaseous state and thicken again as it swings closer. Pluto's moon Charon, meanwhile, has a strange reddish cap at its own north pole, thought to form when methane gas escaping from Pluto's atmosphere drifts across space, freezes onto Charon's surface, and gets chemically transformed by ultraviolet sunlight into reddish organic compounds called tholins, meaning part of Charon's coloring is quite literally made of borrowed Pluto atmosphere. Number 71. Pluto isn't the largest object in its own neighborhood. That title likely belongs to Eris, a Kuiper Belt object discovered in 2005 that turned out to be slightly less massive than Pluto but comparable in size, forcing astronomers to confront an uncomfortable question. If Eris wasn't going to be called a planet, could Pluto keep the title either? That debate led directly to the International Astronomical Union's 2006 decision to create the new category of dwarf planet, which reclassified both Eris and Pluto, along with Ceres, Makemake, and Haumea, all of which are now recognized members of that same class of small, round, but orbitally messy worlds. Number 72. Haumea, one of those other dwarf planets, is one of the strangest shapes confirmed in the solar system, not a sphere at all, but a stretched, elongated ellipsoid, roughly twice as long as it is wide, the result of spinning so fast on its axis, once every 4 hours, that its own rotation has pulled it into an egg-like shape the way spinning pizza dough flattens and stretches outward. Haumea also has its own thin ring system, discovered in 2017, making it the first trans-Neptunian object confirmed to have rings. Number 73. The Kuiper Belt, the region beyond Neptune where Pluto, Eris, Makemake, Haumea, and hundreds of thousands of smaller icy bodies orbit, is actually far more massive and far more populated than the asteroid belt, even though it took until 1992 to confirm the first object out there besides Pluto itself. It's now understood to be the source of most short-period comets, the ones that swing back through the inner solar system on relatively predictable timescales of under 200 years. Even farther out, a handful of extreme objects like Sedna, discovered in 2003, follow orbits so wide and so elongated that at their closest they still stay far beyond Neptune, and at their farthest travel out to nearly 1,000 astronomical units. A pattern of orbits so oddly aligned across multiple such objects that some astronomers have proposed it as indirect evidence for an undiscovered, much larger Planet 9, whose gravity is shepherding them, though no such planet has ever been directly observed. Number 74. Comets are essentially dirty snowballs, mixtures of ice, dust, and frozen gases, and their glowing tails are a direct, visible demonstration of the solar wind and sunlight pushing on matter. As a comet nears the Sun, its ices vaporize into a glowing cloud called a coma, and radiation pressure and the solar wind sweep that material into a tail that always points away from the Sun, not away from the direction the comet is traveling, which means a comet heading away from the Sun after its closest approach is technically flying tail first, dragging its own glowing plume out ahead of it in the direction of travel. Number 75. Halley's Comet, the most famous comet in recorded history, follows a roughly 76-year orbit that carries it between the inner solar system and well beyond Neptune. It's been observed and recorded by astronomers since at least 240 BCE, appears in the Bayeux Tapestry depicting events from 1066, and was the first comet confirmed to be periodic, when Edmund Halley used Newton's new laws of gravity to correctly predict its 1758 return, years after his own death. Its next appearance in the inner solar system is expected in 2061. Number 76. The debris comets leave behind doesn't just vanish once the comet moves on. Comet Swift-Tuttle, for instance, sheds a long trail of dust and gravel along its orbit, and every August, Earth plows directly through that trail, producing the Perseid meteor shower as thousands of pea-sized to sand-sized fragments burn up in the atmosphere at extreme speed. Most meteors people see are no bigger than a grain of rice. The light show comes entirely from friction with the atmosphere, not from the size of the object itself. Occasionally something larger slips through. In 1908, an object thought to be a small asteroid or comet fragment exploded in the atmosphere over Tunguska, Siberia, releasing energy equivalent to roughly 10 to 15 megatons of TNT and flattening some 80 million trees across more than 2,000 square kilometers, without ever leaving an impact crater, since it detonated in the air before reaching the ground. Number 77. Not every object passing through the solar system was born here at all. In 2017, astronomers detected Oumuamua, a small, oddly elongated object moving on a trajectory so fast and so hyperbolic that it could only have come from outside the solar system entirely, making it the first confirmed interstellar visitor ever observed. A second one, Comet 2I/Borisov, followed in 2019, clearly identifiable as a genuine comet, complete with a glowing tail, unlike anything gravitationally bound to our Sun. Both objects were only ever passing through, on trajectories that will carry them back out into interstellar space, never to return. Finally, the true edge, and just how far away it really is. Number 78. Everything discussed so far, every planet, moon, asteroid, and even most comets, sits well within a single light day of the Sun. But the solar system's actual boundary lies far beyond that, in the Oort cloud, a vast, roughly spherical shell of icy debris thought to extend somewhere between 2,000 and 100,000 astronomical units from the Sun, with one astronomical unit being the roughly 150 million kilometers between Earth and the Sun. At its outer edge, the Oort cloud may reach almost 2 light-years out, nearly halfway to the nearest other star system. Number 79. Voyager 1, launched in 1977 and now the most distant human-made object ever built, has been racing outward for nearly 5 decades and crossed into interstellar space in 2012, followed by its twin, Voyager 2, in 2018. Meaning both spacecraft have now left the heliosphere, the bubble of charged particles blown outward by the solar wind. And yet neither has come remotely close to reaching the Oort cloud, the shell of icy debris that marks the solar system's actual gravitational edge. At its current speed, Voyager 1 needs roughly another 300 years just to reach the Oort cloud's inner boundary, and about 30,000 years to fully pass through it. Number 80. Both Voyager spacecraft carry a golden record, a phonograph disc loaded with images, natural sounds, music, and greetings in 55 languages, assembled by a team led by astronomer Carl Sagan, intended for any spacefaring civilization that might one day intercept it. It's a genuinely strange thought. Humanity's most physically distant creations are also carrying, quite possibly, the longest-lasting single artifact of human culture ever made, likely to persist for hundreds of millions of years, drifting through the emptiness beyond our own star. Number 81. Even after traveling for nearly 50 years at over 60,000 kilometers per hour, Voyager 1 is still, on a galactic scale, standing in the driveway. The nearest star system to our own, Proxima Centauri, sits about 4.25 light-years away, roughly 268,000 astronomical units, or 9 times farther than even the outer edge of the Oort cloud. At Voyager 1's current speed, reaching that distance would take on the order of 70,000 years, and Voyager isn't even aimed at it. Everything we just talked about, the Sun, all 8 planets, every moon with a volcano or an ocean or a diamond rainstorm, Every dwarf planet and comet and stretch of the Oort cloud sits comfortably in the innermost sliver of a galaxy containing several 100 billion other stars, most of them, as far as current research suggests, with planetary systems of their own. That covers the headline tour, the version of the solar system most documentaries stop at. But the full picture means going back through the same neighborhood a second time, because plenty of the strangest, best documented details didn't fit the first pass. So here's one more loop, starting back at the Sun. Number 82. The solar wind itself was theorized before it was ever detected. In 1958, physicist Eugene Parker proposed that the Sun's corona should be expanding outward as a supersonic stream of charged particles, a bold claim that many physicists rejected outright, since it seemed to defy the intuition that the Sun's gravity should hold its own atmosphere close. Parker's prediction was confirmed just a few years later, in 1962, when NASA's Mariner 2 spacecraft, on its way to Venus, carried instruments that directly detected the outward streaming particles he had described on paper. That stream is what shapes comet tails, powers auroras, and defines the outer edge of the heliosphere. And Parker's solar probe, the fastest spacecraft ever built, was named in his honor while he was still alive to watch it launch. Number 83. Helium was found in the Sun before it was ever found on Earth. During a total solar eclipse in 1868, French astronomer Pierre Janssen and English astronomer Norman Lockyer independently noticed an unfamiliar yellow spectral line in light from the Sun's chromosphere that matched no known element. Lockyer concluded it had to be something new and named it helium, after Helios, the Greek word for the Sun. It took another 27 years before helium was actually isolated on Earth, extracted from a uranium mineral in 1895. Meaning humanity identified a chemical element in the Sun, 150 million kilometers away, before ever finding a trace of it on the ground beneath our own feet. Number 84. The Sun's outer atmosphere is bizarrely far hotter than its surface. The visible photosphere runs at about 5,500 degrees Celsius, but the corona above it somehow reaches temperatures of 1 to several million degrees, hundreds of times hotter despite sitting much farther from the fusion happening at the core. That reversal defies the basic intuition that things should cool down the farther they get from a heat source, and it remains one of the most stubborn open problems in solar physics, known simply as the coronal heating problem. Leading candidates involve magnetic reconnection, small explosive snaps in tangled field lines, and waves of energy called Ophion waves rippling up from below. And Parker Solar Probe's close passes are gathering data specifically aimed at finally settling the question. Number 85. For decades, the Sun appeared to be producing too few neutrinos. Starting in the 1960s, physicist Ray Davis built a detector deep underground in South Dakota's Homestake Mine, specifically to catch neutrinos, the ghostly particles produced by fusion in the Sun's core, and it consistently registered only about a third of the number solar models predicted. The Sudbury Neutrino Observatory in Canada finally resolved the mystery in 2001, showing that neutrinos actually change identity, or oscillate, between three different types as they travel from the Sun's core to Earth, and Davis's original detector had only been built to catch one of the three. Both results eventually earned Nobel Prizes in physics in 2002 and 2015. Number 86. A total solar eclipse once helped confirm general relativity. When Albert Einstein published his theory in 1915, it predicted that massive objects like the Sun should bend the path of light passing near them, warping space itself. British astronomer Arthur Eddington organized expeditions to Principe, off the coast of West Africa, and to Sobral, Brazil, to photograph stars near the Sun during the total eclipse of May 29, 1919, the only circumstance under which starlight that close to the Sun becomes visible at all. The measured shift in those stars' positions matched Einstein's predicted value rather than the smaller shift Newtonian physics would allow, and the result made headlines around the world overnight, turning Einstein into a global celebrity almost immediately. Number 87. Beyond flares and coronal mass ejections, the Sun regularly produces prominences, enormous, glowing loops and sheets of relatively cool, dense plasma suspended above the surface by the Sun's own magnetic field, some stretching hundreds of thousands of kilometers, far larger than Earth itself. They can hang in place for weeks or months before quietly dissipating or erupting outward entirely, and observers on the ground can see the smaller ones as reddish arcs along the Sun's edge during a total eclipse, once the blinding disk itself is finally blocked out. Back down to the innermost planet for a couple of things that got left out the first time. Number 88. One of the largest, best-preserved impact basins in the entire solar system sits on Mercury. The Caloris Basin spans roughly 1,500 kilometers, blasted out by an asteroid or comet early in the solar system's history. The impact was so violent that seismic shockwaves traveled clean through Mercury's interior and converged on the exact opposite side of the planet, buckling and fracturing the surface there into a jumbled, hilly region nicknamed Weird Terrain, meaning a single ancient collision reshaped Mercury on two sides of the planet at once, thousands of kilometers apart. Number 89. Reaching Mercury is harder than it sounds, because falling toward the Sun means constantly picking up speed. The joint European-Japanese Bepi-Colombo mission, launched in 2018, is threading a looping path involving 9 total planetary flybys, 1 of Earth, 2 of Venus, and 6 of Mercury itself, using each pass to bleed off velocity before it can finally settle into orbit around Mercury in the late 2020s, flying past its actual destination 6 separate times before it's slow enough to stay. Venus has more going on too. Number 90. Venus's solid surface takes 243 Earth days to complete one rotation, but its thick atmosphere doesn't wait around for the ground to catch up. High in the clouds, winds howl at speeds up to roughly 360 kilometers per hour, fast enough to circle the entire planet in only about 4 to 5 Earth days, a phenomenon called superrotation, where the atmosphere spins dozens of times faster than the planet underneath it. Nobody has a fully settled explanation for how it maintains that speed against friction with the surface below, and it remains an open puzzle that missions like Europe's Venus Express and Japan's Akatsuki orbiter have studied directly. Number 91. The Soviet Union's Venera program achieved something nobody has repeated since: multiple successful landings on the surface of another planet under conditions hostile enough to crush and cook most equipment within minutes. Venera 7, in 1970, became the first spacecraft to transmit data from the surface of another planet, and Venera 13, in 1982, sent back the first color photographs of the Venusian surface, a flat, orange-lit landscape of cracked rock slabs, before succumbing to the heat and pressure after just over 2 hours, longer than engineers had actually expected any lander to survive down there. Number 92. In 2020, a team of astronomers announced a possible detection of phosphine gas in Venus's cloud layer, a molecule that on Earth is strongly associated with biological processes, since it's difficult to produce through ordinary geological chemistry alone. The finding reignited a long-standing idea that Venus's temperate cloud layer, unlike its hellish surface, might conceivably host some form of microbial life. Follow-up studies have since disputed both the strength of the original signal and possible non-biological ways phosphine could form there, and the debate remains unresolved. Exactly the kind of open question new missions to Venus planned by NASA and ESA for the 2030s are designed to help settle. Home turf gets a second look as well. Number 93. Circling Earth are two donut-shaped zones of energetic charged particles trapped by the planet's magnetic field, called the Van Allen radiation belts, discovered in 1958 by instruments aboard Explorer 1, the United States' first successful satellite. The inner belt sits roughly 1,000 to 6,000 kilometers up in the outer belt farther out still, and together they're intense enough that spacecraft, including the crewed Apollo missions, had to pass through them relatively quickly to limit astronauts' radiation exposure. Their discovery, made almost by accident when a radiation detector kept reading unexpectedly high counts, is considered one of the first major scientific discoveries of the space age. Number 94. Because the moon is tidally locked to Earth, the same face always points toward us, and the far side remained completely unseen by human eyes until the Soviet probe Luna 3 photographed it for the first time in 1959. The far side turned out to look strikingly different from the familiar near side. It has far fewer of the large, dark volcanic plains called maria, and a much more heavily cratered mountainous crust, a difference planetary scientists still debate the full explanation for, though it's likely tied to differences in crustal thickness between the two hemispheres. Number 95. During a crescent moon, it's often possible to faintly make out the rest of the lunar disk glowing softly, an effect sometimes called the old moon in the new moon's arms. That faint glow is Earthshine, sunlight that bounces off Earth's clouds and oceans, travels back out to the moon, and reflects a second time off the lunar surface before reaching your eyes. Scientists studying the search for life on planets around other stars take Earthshine seriously, since it behaves as a rough stand-in for how Earth's own reflected light might someday look to an alien telescope light-years away. Number 96. The same magnetic field that shields Earth's atmosphere is also what produces the aurora borealis and aurora australis. Charged particles from the solar wind get funneled by Earth's magnetic field lines down toward the poles, where they collide with oxygen and nitrogen atoms high in the atmosphere, exciting them and causing them to release that extra energy as light. Green and red glows mostly from oxygen, blues and purples from nitrogen. Because the funneling happens at both magnetic poles simultaneously, the same storm can trigger mirror-image auroras in the Arctic and Antarctic at once. Mars, unsurprisingly, has more than a handful of facts worth of strangeness left. Number 97. Phobos and Deimos have long been assumed to be captured asteroids, based on their small size, irregular shape, and dark, carbon-rich surfaces that resemble distant asteroids more than Mars itself. But captured asteroid orbits are usually far more tilted and elongated than the Moon's actual nearly circular paths, which has led some researchers to argue instead that they formed the same way Earth's moon did, from debris flung into orbit by a giant ancient impact on Mars. Japan's MMX mission, planned to launch in the late 2020s, aims to land on Phobos, collect a physical sample, and bring it back to Earth specifically to settle the question. Number 98. On certain sun-facing Martian slopes, dark streaks appear and lengthen during the warmest part of the Martian year, then fade again as temperatures drop, a phenomenon called recurring slope lineae. When first identified in 2011, they were widely proposed to be seasonal flows of salty liquid water, since certain salts can lower water's freezing point enough to stay briefly liquid even in Mars's cold, thin atmosphere. Later analysis of their slope angles found they behave more like dry sand and dust avalanches, and most researchers today lean toward a dry explanation, though the debate isn't entirely closed. Number 99. NASA's Curiosity rover, sampling the air inside Gale Crater, has repeatedly detected methane levels that rise and fall with the Martian seasons, and occasionally spike sharply for reasons nobody has fully explained. On Earth, the overwhelming majority of atmospheric methane comes from biological activity, which is exactly why the readings generate so much interest, but non-biological sources, like chemical reactions between rock and water, or methane trapped underground and slowly leaking out, remain equally plausible. Curiosity's sister mission in orbit, the ESA/Roscosmos Trace Gas Orbiter, has so far failed to detect the same methane from above, adding another layer to a mystery that's still open. The debris field between Mars and Jupiter has more to it too. Number 100. After Ceres and Vesta, the next two most massive objects in the asteroid belt are Pallas and Hygiea. Pallas is tilted at a steep angle relative to the rest of the belt and heavily cratered, while Hygiea is nearly spherical, round enough that some researchers have argued it could reasonably be reclassified as a dwarf planet itself, much like Ceres. Together, the four largest asteroids, Ceres, Vesta, Pallas, and Hygiea, account for roughly half the total mass of the entire asteroid belt, even though they're vastly outnumbered by the millions of much smaller objects surrounding them. Number 101. The most primitive meteorites that fall to Earth, called carbonaceous chondrites, contain tiny round grains called chondrules that condense directly out of the swirling disk of gas and dust that formed the solar system, essentially unchanged for 4.6 billion years. Some of these meteorites also contain microscopic prosolar grains, dust particles that condensed around older, long-dead stars before our own sun even existed, meaning scientists can hold, in a laboratory, physical material that is genuinely older than the solar system itself. Number 102. In 2020, Japan's Hayabusa 2 spacecraft touched down twice on the asteroid Ryugu, fired a small projectile to expose fresh subsurface material, and returned samples to Earth in a sealed capsule. NASA followed with its OSIRIS-RX mission, which collected material from the asteroid Bennu and delivered it back to Earth in 2023, giving scientists pristine, uncontaminated asteroid material to study directly rather than relying only on meteorites that had already burned through the atmosphere and sat exposed on Earth's surface. Number 103. NASA's Lucy spacecraft, launched in 2021, is on a 12-year tour designed to fly past 11 small bodies, including, for the first time ever, several of Jupiter's Trojan asteroids. On its way, Lucy made a bonus flyby of a small main belt asteroid called Dinkinesh in 2023, and the images beamed back revealed something nobody expected. Dinkinesh has its own tiny moonlet, itself made of two lobes gently touching each other, a contact binary satellite orbiting alongside a contact binary adjacent asteroid. Number 104. In 2023, astronomers discovered a ring system around Quaoar, a mid-sized dwarf planet candidate out in the Kuiper Belt. But the ring sits roughly twice as far from Quaoar as the so-called Roche limit, the distance inside which tidal forces are thought to be strong enough to keep ring particles from clumping into a moon. Every other known ring system, including Saturn's, sits inside that limit, and Quaoar's doesn't, meaning either the Roche limit isn't as absolute a rule as textbooks describe, or something about Quaoar's rings is stranger than any ring system found before it. On to the giants for round 2, starting with the biggest one. Number 105. Jupiter's moon Amalthea was found in 1892 by astronomer Edward Barnard, using careful direct observation through a large refracting telescope at Lick Observatory. No photography involved, just Barnard's own eyes at the eyepiece. It turned out to be the last moon in the entire solar system discovered that way. Every moon found since has relied on photographic plates and later digital imaging, rather than a human simply spotting a faint point of light drifting near a planet in real time. Number 106. Despite centuries of observation, nobody is entirely sure what actually makes Jupiter's great red spot red. Leading candidates include phosphorus-containing compounds, sulfur compounds, or complex organic molecules dredged up from deeper in Jupiter's atmosphere and altered by ultraviolet sunlight into colored particles. but no spacecraft has ever directly sampled the storm's upper cloud material to confirm which explanation is correct, leaving one of the solar system's most famous features also one of its least chemically understood. Number 107. NASA's Juno spacecraft, in orbit around Jupiter since 2016, used precise measurements of the planet's gravity field to probe its interior structure in a way no previous mission could. Rather than confirming the traditional picture of a small, sharply defined rocky or metallic core, Juno's data suggests Jupiter's core is fuzzy or diluted, with heavy elements gradually blending into the surrounding hydrogen and helium over a large fraction of the planet's radius rather than sitting in a distinct ball, a finding that upended decades of assumptions about how gas giants actually form. Number 108. Beyond the 4 large Galilean moons and smaller inner moons like Amalthea, dozens of Jupiter's confirmed moons are what astronomers call irregular moons. Small, oddly shaped bodies orbiting at huge distances from the planet, many of them backwards relative to Jupiter's own rotation and its other moons. Their tilted, elongated, backwards orbits are the signature of objects captured by Jupiter's gravity long after the planet itself finished forming, rather than moons that condensed alongside it in the original disk of gas and dust. Saturn's rings alone could fill another list entirely. Number 109. 2 of Saturn's smallest moons, Pan and Daphnis, orbit directly inside gaps within the ring system itself. Pan inside the Encke gap and Daphnis inside the narrower Keeler gap, and their gravity actively clears and maintains those gaps, sweeping up or deflecting any ring material that drifts too close. Cassini images even captured Daphnis, raising small vertical waves along the edges of the Keeler gap as it passes, like a boat leaving a wake, visible proof of a moon, actively sculpting a planet's rings in real time. Number 110. During its final orbits in 2017, Cassini discovered that Saturn's rings are steadily raining material into the planet's upper atmosphere. Charged icy particles pulled off the rings by Saturn's magnetic field and funneled down into the clouds below. Based on the measured rate, scientists estimate the rings could be fully gone within a few 100 million years, a relatively short span on cosmic timescales, meaning Saturn as we know it, with its spectacular rings, may be a temporary phase rather than a permanent fixture. Number 111. Saturn's narrow F-ring, a thin, twisted, occasionally braided strand of icy particles, is held together by 2 small shepherd moons, Prometheus and Pandora, orbiting just inside and just outside it. Their combined gravity constantly nudges stray particles back into line, and Prometheus in particular periodically dips close enough to visibly pull streamers of material out of the ring, temporarily distorting its shape before it snaps back into place. Number 112. Titan's thick atmosphere and low gravity, the same combination that makes human-powered flight theoretically possible there, is exactly why NASA selected it as the destination for Dragonfly, a nuclear-powered, drone-like rotorcraft set to launch in the late 2020s. Rather than staying fixed in one spot like a typical lander, Dragonfly is designed to make repeated flights between different sites on Titan's surface, studying its prebiotic chemistry and hunting for the kind of complex organic molecules that might hint at the ingredients for life. The tilted-over ice giant has more going on than just lying on its side. Number 113. In 2023, the U.S. National Academy's Planetary Science and Astrobiology Decadal Survey, the document that guides NASA's major mission priorities for the coming decade, recommended a Uranus orbiter and probe as the agency's single highest priority flagship mission. No spacecraft has visited Uranus since Voyager 2's brief flyby in 1986, and if funded and launched on the timeline scientists have proposed, an orbiter could finally answer basic open questions about Uranus's tilted magnetic field, its odd lack of internal heat, and the makeup of its rings and larger moons. Number 114. Because Uranus takes 84 Earth years to orbit the Sun while tipped almost completely on its side, its seasons are unlike anything experienced on any other planet, and the Hubble and Keck telescopes have tracked dramatic storm activity intensifying as different parts of the planet swing toward direct sunlight after decades of darkness. Observations since the 1990s have shown bright storm clouds appearing and evolving over the course of just days, evidence that Uranus's atmosphere, despite its icy calm blue-green appearance, is anything but static. Neptune, similarly undervisited, still has more to say. Number 115. Because Voyager 2 remains the only spacecraft ever to visit Neptune, planetary scientists have proposed a dedicated follow-up mission called Neptune Odyssey, which would place an orbiter around the planet and drop a probe into its atmosphere, similar to what Galileo did at Jupiter. The concept has been studied by NASA, but not yet formally approved or funded, meaning everything learned about Neptune since 1989 has come exclusively from telescopes on or orbiting Earth, without a single new close-up measurement in over 3 decades. Number 116. Even though Pluto's elongated orbit actually crosses inside Neptune's, the two have never collided and never will, because they're locked in a stable 3-2 orbital resonance. Pluto completes exactly 2 orbits of the Sun for every 3 that Neptune completes. That precise timing means that whenever Pluto's path brings it closest to Neptune's orbit, Neptune itself is always predictably somewhere else entirely, a gravitational rhythm that's kept the two safely apart for billions of years. And out past Neptune, the small, icy, and stranger objects still have plenty left to cover. Number 117. For years after its 2005 discovery, Makemake appeared to be one of the few large dwarf planet candidates without a known moon, until the Hubble Space Telescope spotted a small, dark satellite orbiting it in 2016, informally nicknamed MK2. Its dark, charcoal-black surface stands in sharp contrast to Makemake itself, which is covered in bright, reflective methane ice, making the pair one of the more visually striking odd couples among the solar system's smaller worlds. Number 118. Discovered independently by 2 amateur astronomers in 1995, Comet Hale-Bopp became one of the brightest comets of the 20th century, visible to the naked eye for a record stretch of roughly a year and a half around its closest approach in 1997. Part of what made it so spectacular was its unusually large nucleus, estimated at somewhere between 40 and 80 kilometers across, far bigger than a typical comet, giving it enough frozen material to sustain a bright coma and tail for an exceptionally long stretch of its orbit. Number 119. The European Space Agency's Rosetta spacecraft spent over 2 years, from 2014 to 2016, orbiting Comet 67P/Churyumov-Gerasimenko, watching up close as the comet's activity ramped up and faded with its distance from the Sun. In November 2014, Rosetta released the small lander Philae, which achieved the first controlled landing on a comet's nucleus in history, though it bounced on touchdown and came to rest in a shadowed spot that starved its solar panels, cutting its surface mission short after just a few days of data before its batteries died. Number 120. Between the orbits of Jupiter and Neptune drifts a population of icy bodies called centaurs, named for the mythological creatures because they share characteristics of both asteroids and comets. Their orbits, gravitationally influenced by the giant planets they cross paths with, are inherently unstable over long timescales, and many centaurs are thought to eventually get nudged inward, where rising temperatures start vaporizing their ices and transform them into fully active, short-period comets. Number 121. On New Year's Day 2019, NASA's New Horizons spacecraft, fresh off its historic Pluto flyby, sped past a small Kuiper Belt object called Arrokoth, becoming the most distant object ever explored by a spacecraft up close. Images revealed Arrokoth to be a contact binary, two separate lobes that gently merged together at extremely low speed early in the solar system's history, rather than violently colliding, preserving a shape scientists consider one of the best preserved snapshots of how small bodies originally formed. Number 122. Sedna's extraordinarily elongated orbit already came up earlier in this list, but Sedna isn't alone. Several other extreme trans-Neptunian objects share suspiciously similar orbital orientations, all tilted and aligned in a pattern that would be a strange coincidence if it happened by chance. That shared alignment is the core evidence behind the proposed Planet 9, a hypothetical world perhaps 5 to 10 times Earth's mass that would need to orbit hundreds of astronomical units out to gravitationally shepherd them into place. Though despite dedicated searches with some of the world's largest telescopes, no such planet has ever actually been found. Which brings us, one final time, all the way back out to scale itself. Number 123. Years before the Voyager probes carried their golden records, NASA's Pioneer 10 and Pioneer 11, launched in 1972 and 1973, each carried a small gold-anodized plaque engraved with a simple line drawing of a man and a woman, a diagram of the solar system, and a map showing the sun's position relative to a set of pulsars, an attempt to give any future finder a way to figure out where, and roughly when, the spacecraft came from. Pioneer 10 is now the second most distant human-made object, following behind both Voyagers, and it fell silent in 2003 after more than 3 decades of transmitting. Number 124. Scale the entire solar system down until Neptune's orbit fits on a single sheet of paper, and Voyager 1, the most distant human-made object, humanity's boldest reach outward after nearly 50 years of continuous travel, would still be sitting well within the outer few centimeters of that same sheet. The nearest star system would be roughly 4 kilometers away at that same scale. Every fact in this list, every volcano, every ocean, every ring and storm and impossible orbit, happened inside a bubble of space so small that on a truly cosmic ruler, it barely registers as a point at all. A few of the deepest facts left aren't about any single object at all. They're about the mechanics and the origins tying the whole system together. Number 125. The Sun and every planet orbiting it are thought to have condensed from the same collapsing cloud of gas and dust, a rotating protoplanetary disk, roughly 4.6 billion years ago, which is why every planet orbits in almost the same flat plane and in the same direction. This isn't just theoretical modeling anymore. The ALMA Radio Telescope Array in Chile has directly imaged protoplanetary disks around young stars still forming today, most famously around a star called HL Tauri in 2014, revealing concentric bright rings separated by dark gaps that are widely interpreted as young planets actively carving out lanes in the surrounding material, essentially a photograph of a solar system caught in the act of becoming one. Number 126. Where Earth's water actually came from is still debated, and comets turned out to complicate the leading theory rather than confirm it. Scientists can measure the ratio of ordinary hydrogen to its heavier isotope, deuterium, in water from different sources, and Earth's oceans have a specific, well-measured ratio. When the Rosetta mission measured the water ice on Comet 67P in 2014, the deuterium ratio didn't match Earth's oceans at all, which weakened the case for comets as the primary source and strengthened the case for water-rich asteroids instead, delivered during the earlier, more chaotic stretch of solar system history, when far more debris was slamming into the young Earth. Number 127. Asteroid orbits aren't fixed by gravity alone. Sunlight absorbed by a rotating asteroid gets re-radiated back out as heat slightly later, from a slightly different spot, because the surface keeps rotating in the meantime, and that lopsided heat emission produces a tiny, continuous thrust called the Yarkovsky effect. It's far too small to notice on human timescales, but over millions of years it can shift an asteroid's orbit enough to matter, and modern planetary defense calculations, including the risk assessments for potentially hazardous near-Earth asteroids, now have to factor it in to predict future positions accurately. Number 128. The near-Earth asteroid Apophis, once briefly flagged in 2004 as a genuine possible Earth impactor, will make an extremely close pass on April 13, 2029, coming within roughly 32,000 kilometers of Earth's surface, closer than many geostationary communications satellites, and will be visible to the naked eye from parts of Europe, Africa, and Asia without any telescope at all. Refined orbital tracking, which specifically had to account for the Yarkovsky effect to nail down the prediction precisely, has ruled out any impact risk for at least the next century, turning what was once a genuine scare into what will instead be one of the most watched planetary flybys in history. Number 129. Lunar rock samples brought home by the Apollo missions show a suspicious clustering of impact melt ages between about 4.1 and 3.8 billion years ago, a pattern that led scientists in the 1970s to propose the Late Heavy Bombardment, a hypothesized spike in impacts across the inner solar system during that window, possibly triggered by gravitational upheaval as Jupiter and Saturn's orbits shifted and scattered debris inward. The hypothesis remains debated today, with some researchers arguing the spike is partly an illusion caused by one enormous ancient basin dominating the sample record, but it's still the leading framework used to interpret why so many of the Moon's and Mercury's oldest craters cluster into that narrow slice of deep time. Number 130. Between roughly 1645 and 1715, astronomers recorded almost no sunspots at all, a stretch now called the Maunder minimum, confirmed independently through both historical observation logs and carbon-14 levels preserved in tree rings, since a quieter sun changes how cosmic rays interact with Earth's atmosphere. The Maunder minimum roughly overlapped with the coldest part of a centuries-long European cooling stretch nicknamed the Little Ice Age, and while scientists are careful not to claim reduced solar activity was the sole cause of that cooling, alongside volcanic activity and other factors, it remains one of the clearest historical examples of the sun's output visibly wavering within a human-relevant timescale. Number 131. The idea of a habitable zone, sometimes nicknamed the Goldilocks zone, describes the narrow range of distance from a star where a planet's surface temperature could allow liquid water, not too hot, not too cold. Earth sits comfortably inside the sun's habitable zone, but the boundary is a genuinely fragile one. Climate models suggest early Mars may once have sat near its inner edge before losing its atmosphere, and Venus, despite orbiting only slightly closer to the sun than Earth, likely underwent a runaway greenhouse effect that pushed it completely outside it, meaning our own solar system contains a live before and after example of what happens on either side of that line. Number 132. The metal-rich asteroid 16 Psyche, orbiting in the main asteroid belt, is unusually dense and reflects radar in a way consistent with a surface made largely of nickel and iron rather than rock, leading to the hypothesis that it may be the stripped-bare core of an early protoplanet that lost its outer rocky layers to violent ancient collisions. NASA's Psyche spacecraft, launched in 2023, is on its way to orbit and study it directly, the first mission ever aimed at a metallic-type asteroid rather than a rocky or icy one, in part because it may be the closest thing scientists can study up close to the kind of iron core hidden deep inside Earth itself. Number 133. Saturn's odd, irregularly shaped moon Hyperion doesn't rotate in any predictable way. While nearly every other large moon in the solar system, including Saturn's own, has settled into a stable, synchronous rotation, Hyperion's spin is mathematically chaotic, tumbling unpredictably due to its non-spherical shape and gravitational interactions with nearby Titan, meaning its orientation on any given future date genuinely cannot be calculated in advance, only estimated within a widening range of uncertainty. Number 134. Saturn's outermost major moon, Phoebe, orbits backwards relative to Saturn's other moons and is almost certainly a captured object from much farther out in the solar system, likely a former Kuiper Belt body. In 2009, data from the Spitzer Space Telescope revealed Phoebe sits inside an enormous, extremely faint ring of dark dust, so vast that if it were bright enough to see with the naked eye from Earth, it would appear several times larger across the sky than the full moon. Micrometeorite impacts constantly knock material off Phoebe into that ring, and some of it slowly spirals inward and coats the leading hemisphere of the moon Iapetus, which is the actual explanation behind Iapetus's strange, two-toned coloring described earlier in this list. Number 135. Jupiter isn't the only planet with Trojan asteroids sharing its orbit. Earth has at least one confirmed Trojan, a small asteroid called 2010 TK7, discovered using NASA's WISE Space Telescope, and Mars has several of its own as well, though nowhere near Jupiter's population in the tens of thousands. Smaller planets simply have much weaker, less stable Lagrange points, which makes it harder for objects to stay gravitationally parked there for billions of years without eventually drifting off. Number 136. Telescopes like Kepler and TESS have confirmed thousands of planets orbiting other stars, and the results suggest our own solar system's basic layout. Small rocky worlds close in and gas giants farther out might not even be the galactic norm. The single most common planet size found orbiting other stars so far falls between Earth and Neptune, a category nicknamed subneptunes or super-Earths. And our own solar system doesn't contain a single planet that size at all, which means the most common type of planet in the galaxy might be a type Earth has literally zero examples of to study up close. Number 137. Before Voyager 1 and Voyager 2 ever reached true interstellar space, each first had to cross the termination shock, the point where the solar wind abruptly slows from supersonic to subsonic speed as it starts pushing up against the pressure of the interstellar medium beyond. Voyager 1 crossed it in 2004, and Voyager 2 in 2007, years before either spacecraft finally crossed the heliopause itself, the true outer boundary, and both crossings showed up as a real, measurable jump in plasma density and magnetic field strength recorded by the spacecraft's own instruments, confirming decades of theoretical models with direct, on-the-spot data. Number 138. Real-time solar storm warnings exist, and they depend on a spacecraft parked in a very specific gravitational sweet spot. NOAA's DSCOVR satellite sits at the L1 Lagrange point, a stable location roughly 1.5 million kilometers from Earth directly toward the Sun, where the gravity of the Sun and Earth balance out enough for a spacecraft to stay reliably in place with minimal fuel. From there, DSCOVR watches the solar wind directly and can typically give Earth-based power grid operators and satellite controllers only about 15 to 60 minutes of warning before a given burst of solar particles arrives, making it one of the only forecasts in any branch of science measured in minutes instead of hours or days. Number 139. That same L1 point is only one of 5 Lagrange points in the Sun-Earth system, gravitationally balanced locations first worked out mathematically by Joseph Louis Lagrange in the 18th century, long before any spacecraft existed to use them. The James Webb Space Telescope orbits a different one, L2, positioned on the opposite side of Earth from the Sun, chosen specifically because it lets Webb's tennis court-sized sunshield block heat from the Sun and Earth simultaneously, keeping its infrared instruments cold enough to function without needing mechanical refrigeration. Number 140. Although it was built primarily to study distant galaxies and exoplanet atmospheres, James Webb has repeatedly turned its infrared vision back on our own solar system. In 2022, it captured the sharpest images of Neptune's faint, dusty rings taken since Voyager 2's 1989 flyby, revealing narrow, well-defined ring structures with a clarity no telescope had matched in over 3 decades, along with crisp new views of Jupiter's auroras and its own faint ring system, all photographed almost as an afterthought during a mission mainly designed to look much farther away. Number 141. Uranus and Neptune both have magnetic fields that behave nothing like Earth's, Jupiter's, or Saturn's. Rather than lining up roughly with each planet's rotation axis, Uranus's magnetic field is tilted about 59 degrees off-axis and Neptune's about 47 degrees, and in both cases the field is also offset well away from the planet's actual center. The leading explanation is that their magnetic fields aren't generated deep within a metallic core the way Earth's or Jupiter's are, but in a shallower layer of electrically conductive, slushy ice and water mixed with ammonia, a genuinely different kind of planetary dynamo than anything else confirmed in the solar system. Number 142. The total number of confirmed moons across the entire solar system has now climbed past 300, and more than half of that total has been discovered just since the year 2000. That surge has almost nothing to do with any actual change out in space, and everything to do with steadily improving ground-based digital sky surveys able to pick out smaller, dimmer, more distant objects than ever before, meaning the solar system, even after centuries of study, is still handing over new discoveries every single year, often without a spacecraft anywhere near them. A last handful of loose threads, and then we'll actually wrap this up. Number 143. Jupiter's current orbit isn't necessarily where it started out. The Grand Tack hypothesis, proposed by a team of planetary scientists in 2011, argues that Jupiter originally formed farther out, then migrated inward through the early solar nebula until it reached roughly where Mars orbits today, before Saturn's own formation and migration caught up with it, and the two giants' gravity effectively tacked, reversing Jupiter's direction and dragging it back outward to its current position. The model was built specifically to explain two long-standing puzzles at once: why Mars ended up so much smaller than simulations without a migrating Jupiter tend to predict, and why the asteroid belt contains a mixed population of both dry, rocky asteroids and water-rich ones that seemingly should have formed in very different parts of the disk. Number 144. Sunlight doesn't just shove asteroids along their orbits through the Yarkovsky effect. It can also change how fast they spin. Uneven heating and re-radiation across an irregularly shaped asteroid's surface can produce a slow, steady torque called the YORP effect, gradually speeding up or slowing down its rotation over hundreds of thousands of years. Spun up far enough, a small rubble pile asteroid can start shedding material from its equator entirely, and researchers think this is one of the main ways small binary asteroid systems, a large main body orbited by a smaller moonlet, actually form in the first place, including likely Didymos and Dimorphos, the same pair NASA's DART mission deliberately struck in 2022. Number 145. On a clear, dark night, well away from city lights, it's possible to see a faint, softly glowing pyramid of light rising from the horizon after sunset or before sunrise, tilted along the same track the sun, moon, and planets travel. That glow is the zodiacal light, sunlight scattering off countless tiny grains of interplanetary dust concentrated in the flat plane of the solar system, dust continuously shed by comets and produced by grinding asteroid collisions. It's faint enough that most people never notice it exists at all, even though it's technically the same disk of leftover material that built the planets in the first place, still drifting through the inner solar system billions of years later. Number 146. The Sun's magnetic field doesn't radiate outward in simple straight lines. Because the Sun rotates while continuously blowing out the solar wind, the magnetic field embedded in that wind gets wound into a huge, rotating spiral shape stretching across the entire solar system, nicknamed the Parker Spiral after the same physicist who predicted the solar wind's existence in the first place. It's roughly the same geometry as water spraying from a rotating garden sprinkler, except on a scale of billions of kilometers, and spacecraft navigating the outer solar system have to account for that spiral shape when predicting how and when a burst of solar particles will actually reach them. Number 147. Pluto has 4 small moons beyond Charon, Styx, Nix, Kerberos, and Hydra, all discovered by the Hubble Space Telescope between 2005 and 2012, too small and faint for any ground-based telescope to pick out. Several of them, especially Nix and Hydra, tumble chaotically rather than rotating smoothly on a fixed axis, likely a result of Charon's unusually strong gravitational influence in such a small, crowded system, the same kind of unpredictable tumbling already seen at Saturn's moon Hyperion, suggesting chaotic rotation might be far more common among small, oddly shaped moons than scientists once assumed. Number 148. Titan is actually larger in diameter than the planet Mercury, making it the second largest moon in the solar system after Ganymede, and one of only 2 moons bigger across than an actual planet. It still comes in far less massive than Mercury, though, since Titan is built largely from ice and organic compounds rather than Mercury's dense iron and rock, a reminder that biggest and most massive aren't always the same contest, even when the size difference looks dramatic at a glance. Number 149. NASA's IBEX spacecraft, launched in 2008, doesn't photograph the edge of the heliosphere directly. It maps it by detecting energetic neutral atoms, particles created when fast-moving charged particles from the solar wind collide with slower neutral gas drifting in from interstellar space and swap electrons, briefly becoming detectable, electrically neutral messengers that can travel in a straight line back to Earth. That data has let scientists build the first real maps of the heliosphere's actual shape, and it's turned out to be a genuinely contested question. Early models expected a long cometary tail trailing behind the Sun's motion through the galaxy, similar to a bow shock, but IBEX's measurements suggest the boundary may be far more rounded and bubble-like than that classic picture assumed. Number 150. Most meteor showers produce a steady trickle of a few dozen meteors an hour at their peak, but on rare occasions Earth plows through an unusually dense, recently shed filament of comet debris, and the result is a true meteor storm. During the Leonid shower, tied to debris from comet Tempel-Tuttle, observers in 1833 reported literally thousands of meteors per minute, an event so intense it reportedly convinced some witnesses the world was ending, and a smaller but still spectacular repeat storm occurred in 1966, briefly producing rates estimated at tens of thousands of meteors per hour over parts of North America. Number 151. The most recent widely seen naked-eye comet, Comet NEOWISC, blazed through the inner solar system in the summer of 2020, bright enough to photograph with nothing more than a phone camera on a tripod from suburban backyards around the world. It was discovered by, and named after, NASA's NEOWISC spacecraft, itself a repurposed version of the WISE Infrared Space Telescope originally launched in 2009 for an entirely different survey mission, later reactivated specifically to hunt for exactly this kind of near-Earth object. Number 152. Out in the Kuiper Belt, roughly 1 in every 10 known objects turns out to be a binary system, 2 bodies of comparable size orbiting a shared center of mass, similar to Pluto and Charon but on a smaller scale. That's a far higher binary rate than seen among asteroids closer to the Sun, and it's considered strong evidence that the outer solar system's building blocks originally came together through slow, gentle, low-speed collisions rather than violent, high-energy impacts, since anything faster would tend to shatter such pairings apart rather than let them settle into a stable mutual orbit. A truly final round, and then we're done. Number 153. The late heavy bombardment mentioned earlier has its own detailed explanation, called the Nice model, named for the French city where the researchers who built it were working in 2005. It proposes that Jupiter and Saturn's orbits gradually drifted until the two giant planets crossed a specific gravitational resonance, a moment when Jupiter completed exactly 2 orbits for every one of Saturn's, and that crossing violently destabilized the orbits of Uranus and Neptune, sending both of them migrating outward and scattering a huge portion of the primordial Kuiper belt in every direction, including straight into the inner solar system. It's the same model that ties Jupiter's Trojan asteroids, the Kuiper belt's current sparse population, and the ancient cratering recorded on the Moon and Mercury all back to one shared, chaotic period of giant planet rearrangement roughly 4 billion years ago. Number 154. Titan doesn't just have lakes and rivers of liquid hydrocarbons. Large stretches of its equatorial regions are covered in vast fields of dark, linear dunes, mapped in detail by Cassini's radar since clouds and haze make Titan's surface invisible to ordinary cameras. Unlike Earth's sand dunes, built from tiny fragments of rock, Titan's dunes are made of solid hydrocarbon grains, likely condensed out of the Moon's own methane-rich atmospheric chemistry, and then shaped by wind into ridges that can stretch for hundreds of kilometers, making Titan one of only a few places besides Earth, Mars, and Venus confirmed to have wind-sculpted dune fields at all. Number 155. NASA's Dawn spacecraft, in addition to finding the bright salt deposits already covered on Ceres, also detected ammonia-bearing clay minerals across its surface, a genuine surprise, since ammonia ice only stays stable in much colder conditions than Ceres currently experiences in its position in the asteroid belt. That chemical signature has led some researchers to suspect Ceres may not have originally formed where it orbits today at all, but instead condensed farther out in the solar system, in colder, ammonia-rich territory, before later migrating or being gravitationally nudged inward to its current spot among the other asteroids. Number 156. In 2010, Japan's space agency launched IKAROS, the first spacecraft ever to successfully demonstrate interplanetary travel powered purely by sunlight pressure rather than any onboard engine or fuel. Its thin, square sail, roughly 14 meters across a diagonal, unfolded in space and used the tiny but continuous push of photons bouncing off its reflective surface to actually change and control its trajectory on the way to Venus, proving that a technology once confined to theoretical physics papers could genuinely steer a working spacecraft across millions of kilometers of open space. Number 157. Both Voyager probes are still running on radioisotope thermoelectric generators, power sources that convert heat from the natural decay of plutonium-238 into electricity, and that heat output has been fading by design since before either spacecraft ever launched in 1977. Mission engineers have been shutting down individual instruments one at a time for years now, prioritizing the ones still gathering unique data about interstellar space, and current projections suggest both spacecraft will likely run out of enough power to operate any science instruments at all sometime before the end of the 2020s, bringing humanity's only direct, in-place sensors in interstellar space to a quiet, permanent stop. A very last few, saved for the end because they're some of the best. Number 158. Messenger's mapping of Mercury turned up a surface feature found nowhere else in the solar system: small, irregular, shallow depressions with unusually bright interiors and rims, nicknamed hollows. Unlike impact craters or volcanic vents, hollows appear to form when certain volatile-rich minerals in Mercury's crust are heated intensely enough by the nearby sun that they sublimate directly from solid into gas and escape into space, slowly eating away at the ground from within. Because they show no buildup of small overlapping impact craters on top of them, geologists think hollows are among the youngest surface features anywhere on Mercury, possibly still forming and growing today. Number 159. Of Uranus's major moons, Ariel has the youngest, brightest surface, crossed by deep canyons and smoother plains that strongly suggest past cryovolcanic activity, icy material erupting and resurfacing sections of the moon, much the way lava resurfaces parts of Earth. Almost everything known about Ariel still comes from a single distant flyby by Voyager 2 in 1986, since no mission has ever returned to study Uranus's moons up close since, meaning one of the most geologically interesting moons in the outer solar system has essentially sat unexamined for close to 40 years. Number 160. When New Horizons flew past Pluto in 2015, it found something nobody fully expected out that far from the Sun: a visible blue tint to Pluto's thin nitrogen atmosphere, caused by sunlight scattering off small haze particles high in the sky in a way physically similar to what colors Earth's own sky blue. Closer to the ground, New Horizons also spotted patches of reddish material coating parts of Pluto's surface, almost like discolored snow, tholins, the same kind of organic compounds already mentioned forming on Charon, produced when ultraviolet sunlight breaks apart methane and nitrogen molecules and lets the fragments recombine into complex reddish-brown chemistry. Meaning a world more than 5 billion kilometers from the Sun still turned out to have a sky and a color palette startlingly reminiscent of home. One truly last one, because it ties the whole list back together. Number 161. Every single fact in this video, from the Sun's fusing core to Voyager's fading radio signal, traces back to the same starting point: a slowly rotating cloud of gas and dust, mostly hydrogen and helium left over from earlier generations of stars, that began collapsing under its own gravity roughly 4.6 billion years ago. Almost all of that cloud's mass ended up concentrated into the Sun itself, which is exactly why the Sun still holds 99.86% of everything in the solar system today. The very first fact on this list, meaning the whole 2-hour tour, every volcano, every ocean, every ring and storm and impossible orbit, is really just one collapsing cloud of gas, still working out the consequences of its own gravity, 4.5 billion years later. Every spacecraft mentioned along the way, Parker Solar Probe diving into the corona, Cassini diving into Saturn's clouds, Voyager 1 and 2 pushing out past the heliopause, New Horizons drifting deeper into the Kuiper Belt, exists purely to keep measuring the fallout of that one original collapse, filling in details a rotating disk of dust set in motion long before anything on Earth was alive to eventually go looking for them. And that really is the full tour. That's the solar system, closer, stranger, and far bigger than it has any right to be, all without needing a single invented detail. Just a star, 8 planets, a swarm of moons and dwarf planets and comets, and 4.5 billion years of physics quietly doing things that still sound made up. If even just one single fact in here rewired something in your head, you already know exactly what to do, and I'll see you in the next one.